Hi everyone, in this video I'm going to do an example of trying to use transformations to graph a quadratic. Sometimes this is actually a really easy process if the quadratic is written in the right form, but if it's not written in a form where we can see the transformations, we have to do some slightly messy algebra to get it there. So I'll walk through the messy part. Okay, so I would like to try to sketch f of x is equal to negative 2x squared plus 12x minus 14. Okay, so here's the trouble. Right now what I'm looking at, I see an x squared function and I might be inclined to say that I have a flip over the x-axis and a vertical stretch. But then how the heck do I incorporate the fact that there's an x in here as well? That's not part of the basic x squared function. And the answer is you don't. You can use a wonderful algebra trick to rewrite this in a different form where the x will only show up once instead of showing up in both places, and that trick is called complete the square. So I'll walk you through it. I also have a video posted just of walking through complete the square if you want to see any more examples. But the idea here is basically if we can isolate an x squared and x term, we should be able to cleverly choose a constant to tack onto the end of that, probably not negative 14, but some other constant, that will make it factor into a perfect square. So something like x plus 4 squared or x minus 1 squared, where the whole thing is squared. Okay, so to do this, we need a couple of setup steps. For one thing, I generally just write y as I'm working my way through because I'm lazy and I don't want to have to write f of x over and over again. The setup stuff, this is optional. Depending on what we're doing, sometimes we don't do this. But the way this is written, I can get rid of some of the pieces that I don't like on the right-hand side just by moving them over to the left-hand side. So one of the pieces I don't love right now is the negative 14. I'm going to add it so that it's over with the y. The other thing I don't really like here is the negative 2 attached to the x. When you're completing the square, if you want it to be easy to spot which coefficient is going to work for, which constant is going to work for making your perfect square, you really need the coefficient of x to be 1. It's a lot more challenging if you have a coefficient on x that isn't 1. So I'm going to end up with an x squared minus 6x. Okay, and again, this was all just set up. This was just me manipulating the right-hand side until it gets to a point where it's easy to try to identify the number that turns this into a perfect square trinomial. So I've got a little bit of a mess on the left, and I don't care. I'll deal with that mess after I make my perfect square. I guess I didn't really need to write this in a new step. We'll write up here. If I want to turn this into a perfect square trinomial, the trick is to take half of this number in front of the x and square it. So if I take negative 6 over 2 squared, that's negative 3 squared, which is positive 9. Make sure, as you're doing this, that you do it to both sides. Okay, and here's where you can see if you actually did the right thing or not. When I now go to factor this thing, what I end up with is an x minus 3, x minus 3. So there's the perfect square that I was hoping for. If you aren't sure you got it right, go ahead and just multiply it out and see what happens and see if you got back here. But that would be the plan. If you get a leading coefficient of 1 and then you take half of the coefficient of x and square it, you should end up with a perfect square. There's still a little algebra left to do, but I think it's not too bad. All we have to do now is go ahead and move the mess back over to the right-hand side. So I'm going to subtract the 9. I'm going to multiply everything by a negative 2. Be really careful here. When I say everything, what I'm looking at on this side is a difference between two terms. So here's term number 1 and term number 2. You do have to distribute through differences. So I'll multiply the x minus 3 squared by negative 2, and I will multiply the negative 9 by negative 2. What you do not want to do is distribute the negative 2 into these parentheses. Exponents would have to be applied before you could do any distributing. So just leave it sitting out in front. And then the last step is to subtract 14 from both sides. Okay, so here's what I end up with. And if you'd like to go back to calling it f of x, that's great. This is looking much better for only having one function showing up. I don't have some linear pieces floating around and some quadratic pieces floating around. I have this single squared applying to only one x. So I can say that this would be basic function y equals x squared. And then the transformations I see are a flip. So to get the negative 2 out in front of the x squared term, you'd multiply the entire thing by x squared. So the x squared and x cubed functions are kind of nice because they do have the parentheses built in. So anything inside of these parentheses affecting x, anything outside of them affecting y. If there are no parentheses, then any transformation there affects y. So this is flip over the x-axis. This is vertical stretch by 2, so double all of your y values. This is shift, that one's affecting x's, so it's a shift right, opposite of what it looks like, 3. And then this last one is a shift up 4. Okay, so if you're getting pretty good with your transformations, you're feeling comfortable, feel free to skip through the part where I actually graph these, but I'm going to go ahead and do it for anybody who's still struggling a little and wants to see more examples. So if I want to sketch a graph of this function, I'm going to start with plain old y equals x squared. See if I can make that look a little flatter at the bottom. And I'm going to follow 0, 0. This is a very key point on this graph. Knowing where the vertex is, the little minimum, is a big deal on your final graph. And then I'm going to snag 1 point in quadrant 1. I'll just grab 2, 4. You choose whatever you like. And 1 point in quadrant 3. I'm going to use negative 1, 1. Okay, so again, remember the only rule that you need to worry about is shift last. So I think I'm going to break this up into pairs. I'm going to do the flip upside down and the vertical stretch together. Those go nicely together. And then I am going to do the two shifts together. So flip over the x-axis and vertical stretch, and then shift right and shift up as pairs. Okay, so first, if I do 1 and 2, don't mind my phone. I am flipping upside down, so I have a pretty good picture of that in my head, upside down parabola. And then I'm doing vertical stretch, which is away from the axis, so it's going to stretch it all down further below the x-axis, except for the point 0, 0, which will be stuck. So upside down and steeper. Upside down and taller, but basically that will look like upside down and steeper. Okay, so 0, 0. We can keep track of these even if we want to. If we flip over the x-axis, doesn't move. If we then do vertical stretch, still doesn't move. So this is transformation 1 and 2. So still, as of the first two transformations, we have a vertex at 0, 0. I'm flipping upside down, so the vertex is going to be a max now, but still a vertex. 2, 4. If I flip over the x-axis, it ends up at 2, negative 4, affecting my y's. And then I do vertical stretch, it will end up at 2, negative 8. And then the last point I chose to follow was negative 1, 1. So when I flip upside down, it will end up at negative 1, negative 1. If I then do vertical stretch by 2, it'll be -1, -2. So I have 0, 0, 2, -2, 4, 6, 8. Okay, so 2, -8, and -1, -2. So still a parabola, but upside down and a little steeper. I think I changed my scale a little bit. It doesn't look steeper, but it should be steeper than the first one. Okay, and then I need to do 2 shifts. So shift to the right 3 and up 4. So that's going to push my vertex up into quadrant 1. So I'm going to give myself a little more room in quadrant 1. And let's go ahead and follow that vertex. So if I shift to the right 3, 1, 2, 3, and up 4, it's going to land at 3, 4. So vertex at 3, 4. This point was 2, -8. If I shift right 3, it will land at 5, -8. If I then shift up 4, it will land at 5, -4. Okay, and final point was -1, -2. If I shift to the right 3, it's going to land at 2, -2. If I then shift up 4, it's going to land at 2, 2. So 2, 2. Okay, otherwise it's still parabola opening down. We know its vertex landed at 3, 4. So let's go like this. Like this. All right, and there's my final graph. Thanks for watching.